It is February 3rd, 1943. The heart of Berlin beats with the cold precision of wartime industry. At the Telefunken Research Laboratories in Tempelhof, a small team of engineers gathers around a table under the pale glow of fluorescent lights. The air smells of machine oil and ozone. In the center of the room lies an unassuming copper cylinder, no larger than a coffee mug. Professor Leo Brandt, one of Germany's most respected radio engineers, lifts it carefully from its case. His hands tremble ever so slightly. None of them yet realize that this small object will expose the single greatest intelligence failure of Nazi Germany's radar program. A discovery that would prove the Allies were not merely ahead, but operating in an entirely different realm of science. Just 24 hours earlier, a Royal Air Force bomber, a short Sterling from Pathfinder Force, had been shot down over the Dutch countryside near Rotterdam. The bomber carried a new, highly classified radar system known only to a few within the RAF. It was so secret that it contained explosive charges designed to destroy itself if the aircraft went down. But those charges failed. When German recovery teams reached the crash site, they found the equipment largely intact. The copper cylinder inside, still faintly warm from operation, would become the centerpiece of a scientific revelation. As Brandt studies it, confusion spreads through the room. The device generates power levels at 3 gigahertz, frequencies German physicists had long dismissed as impossible for radar. According to their calculations, it simply couldn't be done. Yet here it was, a compact, elegantly engineered machine that defied every mathematical limit they had sworn by. What the Germans had captured that cold February morning was a British cavity magnetron, the beating heart of the Allies' most advanced radar systems, and it would reveal how far behind the Reich had truly fallen. To understand how this technological chasm came to be, one must go back to 1940, a time when Germany stood at the height of its power. France had fallen. Britain was isolated, seemingly one step away from surrender. In the confidence of that triumph, Adolf Hitler issued a decree that would quietly cripple German science for the rest of the war. No research project, he declared, would receive funding unless it promised military results within 2 years. In the Führer's mind, the war would be over long before then. And so, projects with long-term potential, like microwave radar, were deemed a waste of time. That single bureaucratic decision, made in arrogance, effectively doomed German radar innovation at the very moment it mattered most. At Telefunken, Dr. Wilhelm Runge and his team had already explored the theory behind magnetrons, devices that could generate powerful radio waves in the microwave range. German scientists understood the physics well enough. In fact, as early as 1935, Hans Hollmann had even filed a patent for a multi-cavity magnetron. But their experiments ran into problems. The devices overheated, drifted in frequency, and produced such low power that they seemed useless for real radar. So the Germans abandoned them. They turned instead to longer wavelengths, lower frequencies that were stable and easy to produce with existing vacuum tube technology. By 1942, German radar systems like the Würzburg and Freya were considered among the best in the world. They worked at frequencies between 90 and 600 megahertz, using large parabolic antennas several meters across. These systems formed the backbone of the German air defense network, the famous Himmelbett line that guided night fighters with deadly precision. The Würzburg D radar, with its 3-meter dish, could track aircraft up to 40 kilometers away. Its larger cousin, the Würzburg Riese, the giant Würzburg, stretched that range to 70 kilometers. Freya stations, operating at even lower frequencies, could spot bomber formations more than 150 kilometers from the coast. Together, they created a formidable shield over the Reich. In 1941 and 1942, German radar-directed night fighters tore through RAF bomber streams with chilling efficiency. The Wehrmacht was confident, proud even, that its radar network was unmatched. But that pride would soon turn to disbelief. Because while German engineers had settled for what was possible, British scientists were achieving what their counterparts said could not be done. Late in 1942, strange things began to happen. German analysts noticed that RAF bombers were hitting their targets with uncanny accuracy, even in total darkness or heavy cloud cover. Pathfinder aircraft marked targets with precision that defied explanation. Intelligence officers wondered how the British were navigating so perfectly through the blackened skies of Europe. Then, signals monitoring stations began intercepting mysterious pulses, short bursts of radio waves around 3 gigahertz. German physicists dismissed them as noise or electronic jamming. After all, no one could possibly generate usable power at such frequencies. It was, they insisted, a physical impossibility. But on the night of January 30th, 1943, something extraordinary happened. RAF Bomber Command carried out its first mission using a new device, the H-2S radar. Mounted beneath the bombers in a rotating dish, it painted a live image of the ground below, showing coastlines, rivers, and cities glowing on a green cathode ray screen. For the first time in history, aircrews could see the Earth through cloud and darkness. It was a revolution in navigation, one powered by the very magnetron the Germans had abandoned. Only days later, during a raid on Rotterdam, a Pathfinder Sterling bomber was intercepted by a German night fighter. A burst of cannon fire from below sent the aircraft spiraling down in flames. It crashed near a frozen field, its radar equipment remarkably intact. The Luftwaffe salvage team that arrived before dawn had no idea they had stumbled upon the most valuable piece of technology of the war. When General Wolfgang Martini, head of Luftwaffe Signals Intelligence, examined the wreckage, he immediately recognized the potential significance. The radar's components were unlike anything seen before. Small, compact, built with a precision that seemed almost otherworldly. He ordered the device shipped under armed guard to Telefunken's labs in Berlin. It arrived on February 3, 1943, and was placed on Professor Brandt's desk that same morning. Brandt and his team worked through the night. They photographed every part, measured every dimension, and even used X-rays to peer inside. What they found defied everything they believed about radar physics. Unlike German magnetrons, which required massive external electromagnets, the British version used powerful permanent magnets built directly into its structure. It was compact, elegant, and astonishingly efficient. The craftsmanship was immaculate, tolerances measured in fractions of a millimeter. When the German engineers finally powered it on, the results were staggering. The device produced 10 kilowatts of pulsed microwave power at 3 gigahertz, nearly 1,000 times what their own magnetrons had ever achieved. The output was stable, precise, and repeatable. The room fell silent as the measurements came in. It was undeniable. The British had built something that German theory said could not exist. Brandt's report was clinical, but his words carried an undercurrent of awe. The British have achieved in practice what our mathematics declared impossible. The implications were devastating. In a single moment, Germany's belief in its technological superiority collapsed. The Allies had leapt years ahead. At Luftwaffe headquarters, an emergency meeting was convened. Brandt presented his findings to generals, scientists, and industrial leaders. As he spoke, the room darkened with realization. The British magnetron wasn't an incremental improvement. It was a revolution. It opened the door to compact, high-resolution radar systems that could fit inside aircraft and submarines. The Allies could now see through clouds, detect ships at sea, and find submarines at night. It was not just a new weapon, it was a new way of seeing the world. A working group was immediately formed. The Arbeitsgemeinschaft Rotterdam, or AGR, the Rotterdam Committee. Its mission was threefold: to understand the captured magnetron, to develop countermeasures against Allied centimetric radar, and to create a German equivalent. But each goal proved nearly impossible. The British design relied on manufacturing techniques and materials Germany simply didn't have. The cathodes used special oxide coatings that required precise chemical processes. The permanent magnets depended on cobalt, a metal now in short supply after Germany's invasion of the Soviet Union cut off imports. Even the vacuum seals were beyond German industry's current capability. Every piece of the device revealed another layer of engineering refinement that came only from years of experimentation and mass production. Still, the Germans tried. On February 22, 1943, the AGR gathered in Berlin for its first full meeting. Scientists, engineers, and officers from Telefunken, Siemens, and the Luftwaffe sat around a table examining the captured magnetron. They measured it with calipers, sketched its design, and debated how it could possibly work. One young engineer, Otto Hachenberg, later recalled the moment. "We were holding proof that the British had solved problems we declared unsolvable. Their technology looked like the third or fourth generation of something we had never even begun." In the weeks that followed, interrogators questioned the surviving crew of the downed Sterling. The airmen gave only name, rank, and serial number, as required by the Geneva Convention. But through patient psychological tactics, casual conversation, feigned ignorance, and subtle trickery, the Germans extracted fragments of information. The radar, they learned, was called H2S. It had only recently entered service, but plans were underway to install it on every heavy bomber in the RAF. Then came the truly alarming realization. Reports from the Atlantic confirmed that British aircraft were now detecting and destroying U-boats at night, long before the submarines could dive. The Germans' own radar detectors, designed to pick up the older, longer wavelength Allied radar, were useless against these new centimetric frequencies. U-boat losses began to mount. At the same time, British night fighters equipped with miniature dish antennas were shooting down German bombers over England with deadly precision. The new radar, powered by the same magnetron, was guiding them straight to their targets. In March 1943, irony struck with bitter force. During an RAF raid on Berlin, Telefunken's laboratory, the very site where the captured magnetron was being analyzed, was hit by bombs. The device was destroyed. Weeks of careful study went up in smoke. Yet, fate intervened once again. That same night, another British bomber, a Handley Page Halifax, was shot down in the Netherlands. It carried another H2S radar, almost completely intact. The second magnetron, dubbed Rotterdam Device 2, August 2, confirmed that the British were not working on a few experimental units. These were production models, standardized, reliable, and being fitted to aircraft by the hundreds. Germany tried desperately to copy them. Telefunken engineers began work on their own version, designated LMS-10. But the effort was too little, too late. Manufacturing delays, resource shortages, and relentless Allied bombing made large-scale production impossible. The technological gap could no longer be bridged. While Germany scrambled to understand the science, the Allies were already deploying entire families of magnetron-based radars, H2S for bombers, ASV for anti-submarine aircraft, and AI radar for night fighters. These systems transformed the air war, the Battle of the Atlantic, and ultimately, the outcome of the conflict itself. By the time German engineers finally succeeded in producing a functional copy, the war was turning irreversibly against them. Allied bombers guided by radar devastated German cities. British and American ships, aided by centimetric radar, closed the Atlantic to U-boat operations. And in Berlin, Professor Brandt, who had once held that small copper cylinder with trembling hands, understood what it symbolized. The war for technological supremacy had been lost not on the battlefield, but in the laboratory years before the first shot was fired. When the war ended, captured German scientists and documents revealed how deeply this discovery had shaken the Reich's scientific community. They had learned too late that the Allies' advantage was not luck or espionage, but vision, the willingness to pursue what seemed impossible. In the end, that copper cylinder from a downed bomber near Rotterdam had exposed more than a technological secret. It revealed the true cost of arrogance and the fatal danger of underestimating imagination in wartime. The magnetron would go on to shape the modern world, not just in radar, but in every microwave oven, every telecommunications satellite, every device that transmits and receives signals through the air. But in 1943, it was a weapon of invisible power, one that turned the tide of war and proved that sometimes the smallest things can change the course of history.